Enterprise mainframes routinely process millions of transactions per second, increasingly driven by distributed cloud applications querying legacy data. The platforms servicing these requests have architectural roots decades older than the APIs querying them. Bridging that gap is z/OS Connect. It operates as the gateway, translating incoming REST HTTP calls into legacy protocols that backend systems like CICS or IMS can natively execute. Performance engineers monitor this traffic using SMF123 records. Subtype 1 tracks incoming provider requests arriving from the cloud, and Subtype 2 tracks outgoing requester calls originating from the mainframe. These records yield a precise chronological map of a request's lifecycle. We get exact timestamps for arrival, dispatch, and return, but they omit a critical variable: CPU consumption. Finding the root cause of an API timeout requires synthesizing the SMF123 timestamps with address space utilization from SMF30 and subsystem transaction data from SMF110. A REST HTTP provider request arrives from the cloud, hits the z/OS Connect server, and passes to the backend. Processing time inside the server is tracked as pre-SOR latency. Execution time inside the backend, CICS or IMS subsystem, is logged as system of record time. The server takes the payload back and executes the return trip to the caller, mapping to post-SOR latency. Under baseline conditions, these response times remain flat and predictable, even as request volumes scale upward. Anomalies bloat specific segments of this timeline. A delay in the server looks completely different from a delay in the database. Identifying exactly which segment ultimately degraded dictates whether the middleware team or the database administrators need to investigate. This graph maps request volume against total response time. At 12:30 a.m., traffic is near zero, yet response time spikes to 100 milliseconds. Breaking that spike down reveals under 2 milliseconds spent in the system of record, while 98 milliseconds were pre-SOR latency. The backend CICS region processed the request immediately. The delay originated completely within the z/OS Connect server before the handoff occurred. Because SMF123 records lack CPU profiling, isolating a pre-SOR delay requires extracting address space metrics. This bar chart profiles CPU utilization for the z/OS Connect address space. The server runs almost exclusively on ZII processors, consuming up to 10 milliseconds of CPU per API request. Checking workload manager policies for this specific interval reveals the server and its enclaves were assigned default low-priority service classes. At 12:30 a.m., heavy batch processing jobs kicked off. Because the API server lacked priority, it was starved of ZII dispatch cycles. High pre-SOR latency during low traffic periods points directly to hypervisor queuing and WLM misconfigurations, rather than inefficient application code. This graph maps a different anomaly. During the peak daytime shift at 4 p.m., request volumes climb and response times spike simultaneously. In this breakdown, the pre-SOR latency is negligible. The delay is isolated within the system of record. To investigate the backend, we extract the target application ID and the specific transaction ID, in this case, CSMI, straight from the SMF123 record. We take those identifiers and cross-reference them against SMF110 CICS transaction logs. This comparison maps the incoming API request rate against the CICS CSMI transaction rate. They match perfectly at 0.4 requests per second, confirming this CICS transaction exists solely to service this API. Filtering the CICS performance data exclusively for the CSMI transaction displays its specific response profile during the 4 p.m. interval. The profile highlights a massive expansion in the metric tracking time spent dispatched but not using CPU. The CICS region was experiencing severe CPU starvation on the QR and L8 task control blocks, artificially inflating the soar time for the API. This logic applies in reverse when the mainframe operates as the requester, initiating outbound calls to cloud-based APIs. These outbound calls generate SMF123 subtype 2 records, tracking the application as it requests external resources. Subtype 2 records include an additional timestamp logging exactly when the call leaves the mainframe, allowing us to calculate external network transit latency. Whether incoming or outgoing, diagnosing a system of record delay requires pulling subsystem-specific SMF110 data to uncover transaction-level resource starvation. SMF123 records identify precisely when and where a delay occurred, but they lack the metrics to explain why. This diagram illustrates the three-tier observability matrix required for diagnosing API performance. When a delay registers as pre-SOR latency, engineers bypass the subsystem entirely and audit address space metrics in SMF30 and WLM policies. When the delay occurs within the system of record, the workflow mandates crossing into SMF110 data to hunt for subsystem bottlenecks and CPU starvation. Layering these records turns a timeout alert into a precise intervention at the hypervisor or the subsystem level.